Welcome back to another video of our course on probability theory. We now know what convergence of random variables is, and today we are turning to the so-called Borel-Cantelli lemma, which you might have heard of in your basic course on probability theory. It is dealing with a situation where some experiment or something is repeated infinitely many times. So let's say a coin toss or something. And you're asking yourself, well, what's the probability that, for example, infinite many coins come up heads? The answer is 1 in this example, but there are other examples where, for example, the events are not independent or maybe are not identically distributed, where that might not be the case. And this is answered essentially by the Borel-Cantelli lemma, how you compute this. Let's see what it means. So, the Lemma of Borel and Cantelli. This is actually the first time we really talk about independent random variables, but of course you know them from the basic probability course. And let's first of all define them, because that has changed a bit from the basic course in probability theory, because we now have sigma algebras and stuff. So this here you know. Independence means that the probability of an intersection of sets is the product of the probabilities. That's as usual, but here it's already a bit different, because I here can be arbitrary, which means it can be infinite. So I can be infinitely large, and in this case we require this here only for finite subsets of I. So the subset index f means a finite subset. So that's the first change. The second change is that we can also say set systems, Ci, are independent. So set systems are independent if this formula holds here for all Aj in Cj, for all j in j. So replace this here, we basically say for all Aj in Cj, j from 1 to j in j. Aj in Cj, j in j, and j is a finite subset of I. So this is for set systems, for example, sigma algebras. We call them independent when this here holds. Let's grab this here. And last, random variables are called independent if their generated sigma algebras are independent. Okay. Well, there are some basic things. Random variables are called independent if and only if, for all finite subsets, the joint distribution of xi is the product measure. The product measure means computing probability that x1 is something, x2 is something, and so on. It's just the product of the probabilities. So that's how the product measure is defined. And let me also mention, in the course measure theory for probabilists, which you also know, there is one whole section about measures on products, and how exactly this product here is defined you can read there. And in this section in measure theory there is one theorem called Kolmogor's extension theorem at the very end, which we need for this corollary. I'm also not going to show this as a proof, but I'm explaining to you what it is here. The question is, if you have, well, distributions or random variables on some sets, so this is capital I. So if you have random variables xi, is there a probability space such that they are independent? So can I construct a very complicated probability space so that all the xi's here, or as it's said here, yi's, which are identically distributed, here, identically distributed, such that they become independent. And the answer is, well, if they have values in a Polish space, then yes, that's possible, no matter how complex, so how large the I here is. So that's a positive answer. And essentially what is not written there, but also holds, that even holds if E is not Polish, but I'm not going to show this here. And then I'm also not going to show this in the measure theory course, because basically all spaces we have are Polish, so that's not really a restriction. So you can now remember, no matter how complicated the index set is here, you can construct always independent random variables. Yeah, that for example means you can take xi, I from the real numbers, normally distributed random variables, which are all independent. So there are uncounted many in n0, 1 random variables. Okay, then next basic lemma. If we have xi's which are independent, and we have phi i's to some other measurable space, and they are measurable, then also the functions phi I of xi are also independent. And that means, for example, if x and y are independent, then, for example, also x squared and e to the power of y are also independent. Which is then nice, of course. And the proof is very simple, actually. And the reason is, if I have phi I of xi and the generated sigma algebra of this, so I take a set from this here, so I have to make the inverse of this function here applied to some set in omega I double prime. And since phi I is measurable, that's a subset of a measurable subset of phi I prime, and pull that back gives a measurable subset of anyway of f, so on your basic probability space, but that's not what we need. So what I have is that this here is a subset of sigma of xi. And the reason, well, this here consists of all pre-images of phi I times xi, and this here consists of all pre-images of xi, and clearly this is here a subset of this, because phi is measurable. So that's not hard. Another thing that you know from your basic probability course is if two random variables are independent, they are also uncorrelated. And that means that the expectation of the product is the product of the expectations. Well, the proof of this here, okay, if x is an indicator and y is also an indicator, because x times y is then the indicator of A intersected with B, and here's the probability of A and here's the probability of B, so that's just the definition. Then in a second step you can show if this formula holds, for example, for the simple function, it also holds for sums, because the expectation of a sum over xi and a sum over yj is by linearity of the expectation, sum over ij, expectation of xi yj, I assume I have shown this here already for the single ones. So this is here the sum of I and j expectation of xi, expectation of yj. And now I can pull apart the sum of expectation of xi times sum of all j expectation of yj, which means, well, it holds also for the sum. Okay, of course I have to then also use linearity again and write the sum inside of the expectations, like this here. So that means, since I have shown this here for these indicator functions, I can say it's now also okay for simple functions. So linear combinations of indicator functions. And then by an approximation argument, which I'm not going to involve here, for non-negative measurable functions. So this follows the steps which you often do in measure theory, where you first show something for simple functions and then use an approximation argument, and show this for non-negative measurable functions by using the theorem of monotone convergence on both sides. Okay, and that means we have shown this old result again. But beware, and you know this already, if two random variables are uncorrelated, they don't have to be independent. And here's an example. Two very simple things. X and y can be 0 and 1, both with probability a half. And I can have x plus y and x minus y. And it's an easy computation that the expectation of x plus y times x minus y, which is by the binomial formula the same as expectation of x squared minus y squared, which is by linearity of the expectation of x squared minus the expectation of y squared, which is 0 because both have the same distribution, which means they are uncorrelated, but they are not independent. You can choose whatever you like here, essentially. So I took here the example x plus y equals 2 and x minus 1 equals 1. Sorry. Which is 0. Because x plus y equals 2 can only happen if both x and y are 1, but then x minus y must be 0. So certainly this probability is 0, which is not 1 over 16, which is the probability I claim that x equals y equals 1 times x equals 1, y equals 0. So all of these pairs have probability 1 over 4 anyway, because I have two random variables both come up 0 or 1 with probability a half. And when you look at this here, that's the probability that x plus y equals 2. And this is the only case where x minus y can be 1. Because for x minus y equals 1, x must be 1 and y must be 0. And now we see they are not independent. And now we come to the main thing of the video of today, which is the Borel-Cantelli lemma. And that might be part of your, might have been part of your basic probability course, but it's not part of all these courses. First I have to define something. So that's a strange thing, essentially. Lim sub of a sequence of sets. So ANs are sets here, and I define the lim sub. so the largest limit, so to speak. And how is that defined? Well, let's just say AM, just to imagine something. AM is the event that an mth trial of a random experiment is a success. AM is mth experiment is a success. The union MO bigger or equal to N, AM, is the event that in some experiment with a number bigger or equal to N, a success occurs. So that's this here. And intersection over all N means no matter how many experiments you already did, there will be another success with a higher number in the experiment number. So for all N, there will be an M such that you have a success at a later experiment. So that's this here. There is also a lim_inf, which is just defined the other way around. So have a union over intersections, which is something completely different. Well, here. The Borel-Cantelli lemma has two parts. And it says that the probability of this lim sub here is either 0 or 1. It's 0 if you can show that the sum of all these probabilities is finite. And if you can show that it's infinite, then the probability is 1 of the lim sub. If you can show that the AIs are independent. So that's important, as we will see in an example. Let's prove that here. And on this slide, I'm only proving the first assertion here. And on the next slide, I'm doing the second. The first one, that's a one-liner. Lim sub AN, and the probability of this. So the lim sub is an intersection of unions. And when you look at these unions here, this index set here becomes smaller and smaller the larger n gets, which means that this here is a decreasing sequence. And since measures are continuous, you can use this and write that's the limit. N goes to infinity. Probability that the union of AMs, M bigger or equal to N, holds. As you know, probability of a union is less or equal than the sum. Sum M from N to infinity, P of a M. In the first part, we have that this sum here converges, which means when you started at a very late thing here, a very late index, and some from this here, like I do here, I have convergence to 0. So this thing here converges to 0. And I have shown the first part. The second part is a bit more complicated. I need here independence. So before we start, there's one inequality which I need. Log 1 minus x is smaller or equal than minus x for x in 0, 1. So what does this mean here? Let's plot x here and log x here, as you know. This is like this. And you can also compute that here you have the derivative of 1. So this here is the log. And this here is the function x minus 1, log x minus 1, which means, that holds everywhere, but in particular also in the area between 0 and 1. So log x is smaller or equal than x minus 1 we have here. And now we say, let's define y is 1 minus x. And then we have log 1 minus y is more or equal to minus y. So just by changing the parameters here, which is this here when I change back the y to the x. So, okay, that's calculus. And we need it in the following calculation. I have to show that the probability that of this here equals 1. And it's the same to show that the lim sup of an complement equals 0. Okay, let's write it down. Lim sup was the intersection of the union. I make the complement, then that's the union of the intersections, m bigger or equal to n, of the complements. Again, you can see that this here is increasing now, because the intersection goes over fewer and fewer indices. By continuity of measures, that's the same as lim n goes to infinity, probability of an intersection, a complement, m from n to infinity. Now I can use the independence and I have the probability of an intersection. We only require this for finite index sets, but I can extend this here to an infinite index set by an approximation argument. So limit n goes to infinity, product m from n to infinity, probability of the complement of am, so 1 minus probability of am. And now we have it. Log of this here is smaller or equal to this. Well, but we do not have a log here, but we can smuggle one in by writing that the exponent of the logarithm equals identity. So I have limit n goes to infinity, product over, well, this here is exp log 1 minus p of am. Product over exps is exp over sum m from n to infinity, log 1 minus p of am. Exp is monotone, and log of 1 minus x smaller than equal to minus x means it's more or equal to e to the power of minus sum. Sorry, I forgot a limit here. I forgot a limit here. Limit n goes to infinity, m from n to infinity, p of am. Since this here is infinity, well, I can also start at m and it stays infinity. So this here is infinity for all n, which means that this here is e to the minus infinity, which is 0. And we are done, because we have shown that the probability of the complement of this here is 0. Okay, so we have it for the Borel-Cantelli lemma. Typo. Let's make just a simple example. we have an infinite p coin toss. So we have had occurs with probability p. And we want to see why there will be infinitely many heads. Let an be the set xn is head. Then I have a1, a2, and some independent. And the sum over p of an, which is what we have to compute here in order to apply the Borel-Cantelli lemma, n from 1 to infinity, is the sum over p's, which is infinity. And what does that mean now? So that's infinity. The probability of the lim sub Rn equals 1, which means there will be infinitely many heads in these infinite sequence. Next example here. It's important in this calculation that we're doing here that the events are independent, because I could, for example, say here Bn equals is the set that x1 is head for all n. So either Bn occurs for all n or for no n, because it only depends on what x1 is. So the probability that infinitely many of these events here occurs is p, because if x1 comes up head, all of the bn's occur, and that's p. And in particular, it's not 1 if p is not 1. So the independence is, of course, violated here, because the bn's are not independent. They're absolutely dependent. Okay, here's the last example, which is the only non-trivial one. Assume you have a geometric p distribution. So, for example, you try over and over again to have a 6 when you roll a die. You record x1, that's how long it took for you in the first attempt. x2, how long it took in the second attempt. x3 in the third attempt, and so on. And you say that something, the nth event occurs if in the nth trial it took longer than n. So the first one, it took longer than 1, but in the 1000th attempt, it takes longer than 1000 attempts to throw a 6. And you can ask yourself, do these events occur finitely often or infinitely often? Well, we know what we have to do here to use the Borel-Cantelli lemma. So the xn's here would be independent. That means we can use both directions. And we have to compute the probability of an summing over all n. Well, that's the sum over the probability that xn is bigger than n from 1 to infinity. How is that? The probability that it takes me at more than n trials to get a success, that's 1 minus p to the power of n from 1 to infinity. Yes, like this here. And that's certainly a geometric series which is finite, which means this here only occurs finitely often. Okay, that's it for today, and next time we will show something related to what we had today. We saw here's a 0, here's a 1, and there were hardly any thing in between. So in one example, we had something like a P here, but in this example, the ANs have not been independent. And the Kolmogorov 0-1 law, which we'll have next time, states that if events are independent, this probability can either be 0 or 1, but nothing in between. Okay, see you then.